Welcome to this walkthrough of LeetCode problem number 2184, number of ways to build sturdy brick wall. In this session, we'll explore how to approach this problem step by step, break down the logic, and understand the nuances of constructing sturdy walls. Let's dive in and solve this together. In this problem, you are tasked with building a brick wall of a given height h and width w using rows of bricks. These bricks come in two sizes, width 1 and width 2. Each row of the wall must be completely filled, meaning the total width of the bricks in a row must always equal w. Now, a wall is considered sturdy if the vertical seams or the gaps between bricks do not align between adjacent rows. So, when constructing the wall, you need to ensure that the seams in one row are offset from the seams in the row beneath it. The goal is to determine the total number of different ways to build such a sturdy brick wall, and because the number can be very large, the result must be returned modulo 10⁻9 plus 7. The input consists of two integers, h, the height of the wall, which can go up to 1000 rows, and w, the width of the wall, which can be as large as 10 units. The output is a single integer representing the number of valid configurations for the sturdy wall under these constraints. Let's look at a concrete example to understand how this works. Suppose the height of the wall h is 2, and the width w is 3. First, we generate all possible rows of bricks for a width of 3 using the given brick sizes. These rows include 1, 1, 1, where all bricks are of width 1, 1, 2, where a brick of width 1 is followed by one of width 2, and 2, 1, where a brick of width 2 is followed by one of width 1. Next, we build the wall row by row, ensuring that no vertical seams align between adjacent rows. For example, if one row is 1, 2, and the row above it is 2, 1, the seams do not align, and the configuration is valid. However, if both rows are 1, 2, the seams align, and the wall is not sturdy. After calculating all valid configurations for two rows, the result is 4. This means there are 4 ways to build a sturdy wall of height 2 and width 3. Now consider another example where the height of the wall h is 3, and the width w is 2. For this width, the possible rows include 1, 1, where both bricks are of width 1, and 2, where a single brick of width 2 fills the row. When constructing the wall, rows must be stacked in a way that no vertical seams align between adjacent rows. After exploring all valid arrangements for 3 rows, we find that there are 2 distinct ways to construct a sturdy wall of height 3 and width 2. This gives us the output of 2 for this example. To summarize, the constraints of the problem ensure that the height of the wall h can go up to 1000 rows, and the width w can be as large as 10 units. The result must always be returned modulo 10⁻9 plus 7 to handle the potentially large numbers. It is important to consider edge cases. For example, if the height h is 1, the wall consists of a single row, and the result is simply the number of valid row configurations for the given width w. Similarly, if the width w is 1, there is only one valid way to build the wall, using only bricks of width 1. Finally, when both h and w are at their upper limits, the solution must be efficient in terms of both time and memory to handle the large potential search space without exceeding computational limits. To solve the problem of determining how many sturdy walls can be constructed with given dimensions, we need to address the challenge of ensuring that no vertical seam aligns between consecutive rows. A brute force approach might seem intuitive at first. Here, we enumerate all possible row configurations that fit the given width using bricks of size 1 and 2. Then, for each combination of rows, we check if the wall is sturdy by verifying that no vertical seams overlap between adjacent rows. This can be implemented using recursion or bit masking to generate all valid rows. However, this approach quickly becomes infeasible due to its exponential complexity. For every row, we have 2 to the power of the width possible configurations, and verifying a wall of height h multiplies the computation further. This makes the brute force approach impractical for larger inputs, as the number of configurations grows exponentially. Instead, we consider a more efficient solution that leverages dynamic programming. Dynamic programming offers a more optimized approach by focusing on valid row configurations and the transitions between them. The key insight here is that each valid row can be represented as a unique bit mask that encodes its vertical seam positions. We can pre-compute all valid row configurations for a given width and determine which pairs of rows can transition without overlapping seams. The dynamic programming state can be defined as dp r mask, where r represents the number of rows constructed so far, and mask represents the seam configuration of the current row. The transition rule allows us to build the state row by row. If two masks, mask 1 and mask 2, are compatible, the number of ways to reach the current state is updated using the values from the previous state. This approach is efficient because the number of valid rows and transitions is much smaller than the total possible configurations, and the time complexity is proportional to the product of the height and the number of transitions. By pre-computing valid rows and transitions and using this dynamic programming framework, we achieve a solution that is both computationally efficient and scalable, making it a suitable choice for this problem. We selected the optimized dynamic programming approach because it strikes a balance between efficiency and ease of implementation. By using bit masking to represent rows and pre-computing valid transitions, we significantly reduce computational complexity compared to brute force methods. This makes the approach well suited for larger inputs, where exponential growth would otherwise be a limiting factor. Additionally, this strategy is flexible and can be adapted to accommodate new constraints if needed. While it does require more memory to store the valid rows and their transitions, the trade-off is worthwhile given the efficiency gains. Mathematical alternatives, such as matrix exponentiation, might offer theoretical advantages but are harder to implement and debug in practice for this problem. Dynamic programming provides a clear, robust, and scalable solution that aligns well with the problem's constraints and requirements. To tackle the problem of building a sturdy brick wall, we start by breaking it down into manageable steps. The main challenge is to ensure that no vertical seam in one row aligns with a vertical seam in the row directly above it. First, we need to understand the constraints. The wall has a height h, a width w, and is built with bricks of widths 1 and 2. With these constraints in mind, the next step is to generate all possible configurations for a single row. A row configuration specifies where the vertical seams are located, and we can use a backtracking approach to systematically generate all valid configurations for a given width w. For example, if w is 4, a valid configuration could place seams at columns 1, 2, and 3, represented as 1, 2, 3, or seams at columns 2 and 4, represented as 2, 4. A key insight here is to use binary masks to represent these configurations efficiently. For instance, a mask like 1100 would indicate seams at positions 2 and 3. Once we have the row configurations, the next task is to determine which pairs of rows are compatible by checking that their seams do not align. This information is stored in a compatibility graph for efficient state transitions later in the algorithm. After generating all valid row configurations, the compatibility graph is built by iterating through all pairs of row configurations and checking whether they are compatible. Two rows are compatible if no seam in one row matches the position of a seam in the other row. This compatibility information is stored as a graph, where each node represents a row configuration and edges represent compatibility between configurations. Next, we apply dynamic programming to compute the number of ways to build the wall. Let dp I mask represent the number of ways to construct a wall of height I such that the top row has the configuration represented by mask. The base case is straightforward. For height I equals 1, we initialize dp 1 mask equals 1 for all valid masks. The transition relation is key. When building the wall row by row, the value of dp I mask 1 is computed by summing over all dp I1 mask 2 for configurations mask 2 that are compatible with mask 1. This ensures that no vertical seams align between adjacent rows. Finally, the result is obtained by summing all dp h mask values for the last row. Since the number of ways can grow very large, we use modulo arithmetic with a modulus of 10⁻9 plus 7 to keep the computations manageable and prevent integer overflow. Dynamic programming is essential here because it drastically reduces the complexity of the problem compared to directly generating all possible wall configurations. By breaking the problem into smaller states and storing intermediate results, we avoid redundant calculations. Modulo arithmetic is applied throughout the calculations to ensure that the results remain within the bounds of standard data types. The data structures used in this solution are carefully chosen for efficiency. Binary masks are used to represent row configurations compactly, allowing fast bitwise operations to check compatibility. The compatibility graph is stored as an adjacency list, which makes it easy to traverse and retrieve compatible configurations during the dynamic programming transitions. Lastly, the DP table itself is a 2D array where each entry DP, I, mask, represents the number of ways to build a wall up to height I with a specific top row configuration. These structures work together to efficiently manage both time and space while solving the problem. The algorithm's complexity is primarily determined by the number of row configurations and the height of the wall. Generating all possible row configurations has a time complexity of O2 to the power of W, as each width W can yield up to 2-W binary masks. Constructing the compatibility graph involves checking pairs of configurations, resulting in a complexity of O2 to the power of W(2). The dynamic programming step involves computing transitions for each height h and pair of compatible configurations, leading to a complexity of O(h times 2 to the power of W times 2 to the power of W). Overall, the total time complexity is O(h*2)(2W), which is feasible for small values of W. The space complexity includes storage for the compatibility graph, which requires O(2 to the power of W(2), and the DP table, which requires O(h*2 to the power of W. Therefore, the total space complexity is O(h*2 to the power of W plus 2(2W). Both time and space usage are manageable for small widths, making this approach practical for solving the problem within the constraints provided by the LeetCode environment. To solve the problem of building a sturdy brick wall, we start by importing the ru_cache decorator from the functools module to optimize our recursive calls. The build wall method takes two parameters: height, which is the number of rows in the wall, and width, which is the total width of each row. We define a constant mod to ensure our results fit within the required limits. The first step is to generate all possible row configurations that fit the specified width. This is achieved using a helper function called generate_row_configs. Inside this function, we use a backtracking approach to explore possible combinations of bricks of size 1 and 2. By recursively adding bricks, we check if the total width equals the desired width. If it does, we store the configuration as a tuple in the configs list. Once all valid configurations are generated, they are returned and stored in the row_configs variable. These configurations represent the building blocks for constructing the wall. The next step is to determine how these rows interact with each other. To ensure that the rows align properly in the wall, we define a function called r_compatible. This function checks if two row configurations can be stacked without any vertical seams aligning. First, we compute the positions of the seams for the first row by summing the widths of its bricks and storing these positions in a set called seams1. Then, we calculate the seam positions for the second row and check if any of these positions overlap with those in seams1. If there's an overlap, the rows are incompatible, and the function returns false. Otherwise, it returns true. With this compatibility function, we pre-compute an adjacency list for all row configurations, where each configuration is linked to the rows it can stack with. This adjacency list is crucial for building the wall dynamically. Now, we use dynamic programming to count the number of ways to construct the wall. The DP function, decorated with ru_cache for memoization, takes two parameters: the current row index and the remaining height of the wall. If the height is reduced to 1, there's only one way to place the final row. Otherwise, we iterate through all compatible rows from the adjacency list and recursively calculate the total number of ways to build the remaining wall. In the dynamic programming function, as we calculate the total number of configurations, we ensure the result is always modulo mod to prevent overflow. Finally, we compute the overall result by iterating through all possible starting rows and summing up the ways to build the wall starting with each one. Again, we take modulo mod at each step to keep the result within limits. Once all rows are considered, the total number of ways to build the wall is returned as the result. This approach efficiently combines pre-computed row configurations, adjacency relationships, and dynamic programming to solve the problem within the constraints. By leveraging memoization and modular arithmetic, we ensure that the solution is both optimal and scalable for large inputs. Here, we start by defining our solution class and a constant mod, which will be used to handle large numbers during calculations by performing modulo operations. The first method, generate_row_configs, is designed to generate all possible row configurations that fit a given wall width. This method utilizes a helper function called Backtrack, which performs a depth-first search to build combinations of row layouts. Each row is constructed by sequentially adding bricks of size 1 or 2. If the total length of bricks matches the specified width, the current combination is added to the list of valid configurations. Otherwise, the function continues exploring by adding another brick. This approach ensures that all possible arrangements of bricks that align with the given width are accounted for efficiently. Next, we define the R-compatible method, which checks if two rows can be stacked on top of each other without overlapping seams. To achieve this, we calculate the seam positions for the first row by iterating over its bricks and maintaining a running total of their lengths. These seam positions are stored in a set called seams1. Then, for the second row, we check each of its seam positions against seams1. If any seam from the second row matches one from the first row, the rows are deemed incompatible, and the method returns false. Otherwise, it returns true. After this, we move to the build wall method, where we start by generating all valid row configurations for the given wall width. We also initialize an adjacency list to store pairs of rows that are compatible. For each pair of row configurations, we use the R-compatible method to determine whether they can be stacked together, and if so, we add their indices to the adjacency list. Finally, we use dynamic programming to calculate the total number of ways to build the wall. The DP array is initialized to keep track of the number of ways to form walls of various heights using specific row configurations. In the base case, we set all configurations for height 1 to 1, as any row can form a wall of height 1 by itself. For greater heights, we iterate through all row configurations and use the adjacency list to find compatible rows from the previous height. For each valid pair, we update the DP value for the current height by adding the contributions from the previous height, ensuring to take the modulo at each step to prevent overflow. Once the DP table is fully populated, we calculate the final result by summing up all the ways to build the wall of the given height using any row configuration. The result is then returned as the total number of ways to construct the sturdy brick wall. To solve this problem, we first need to generate all the valid row configurations for the given width of 3. By using bricks of size 1 and 2, we can create the following configurations: 1, 1, 1, where we use 3 bricks of size 1, 1, 2, where we use 1 brick of size 1 followed by 1 brick of size 2, and 2, 1, where we use 1 brick of size 2 followed by 1 brick of size 1. Next, we pre-compute the adjacency relationships between these rows. Two rows are considered compatible if their seams do not align. For instance, 1, 1, 1 is compatible with all other configurations because it has no overlapping seams with them. Using this logic, we build an adjacency list. Row 0, 1, 1, 1 is compatible with rows 0, 1, and 2. Row 1, 1, 2 is compatible with rows 0 and 2, and row 2, 2, 1 is compatible with rows 0 and 1. Now that we have the adjacency list, we use dynamic programming to calculate the number of ways to build the wall. We define DP, row, remaining underscore height, as the number of ways to build the wall with remaining underscore height rows starting from the given row. The base case is straightforward. If there is only one row left to build, there is exactly one way to place the top row, so DP, row, 1, equals 1. For the recursive case, DP, row, remaining underscore height, is the sum of DP, next underscore row, remaining underscore height 1, for all rows next underscore row compatible with the current row. Let's compute this step by step for a height of 2. For row 0, 1, 1, 1, dp 0, 2 equals dp 0, 1 plus dp 1, 1 plus dp 2, 1, which is 1 plus 1 plus 1 equals 3. For row 1, 1, 2, dp 1, 2 equals dp 0, 1 plus dp 2, 1, which is 1 plus 1 equals 2. For row 2, 2, 1, dp 2, 2 equals dp 0, 1 plus dp 1, 1, which is 1 plus 1 equals 2. Adding these together, the total number of ways to build the wall is 3 plus 2 plus 2 equals 7. Now let's consider a wall with height 3 and width 4. First, we generate the row configurations for width 4 using bricks of size 1 and 2. The valid configurations are 1, 1, 1, 1, 1, 1, 2, 1, 2, 1, 2, 1, 1, and 2, 2. Next, we determine the compatibility between these rows. For example, 1, 1, 1, 1 is compatible with 1, 2, 1 because their seams do not overlap, but it is not compatible with 2, 2, because both have seams aligned at the same positions. After pre-computing the adjacency list, we apply the dynamic programming approach. For a wall of height 3, we calculate dp, row 3, by summing up dp, next underscore row 2, for all compatible rows next underscore row. This process is repeated for each row, and the final result is obtained by summing up all dp, row 3, values for the rows. The total number of ways to build the wall for height 3 and width 4 is the sum of all dp, row 3, values we calculated. This gives the final output for this example. Now, let's consider another example, a wall of height 1 and width 5. For this case, we first generate all valid row configurations for width 5. These include 1, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 1, 1, 2, 2, 2, 1, 2, and 2, 2, 1. Next, we compute the adjacency list. For instance, 1, 1, 1, 1, 1 is compatible with 1, 2, 2, because there are no overlapping seams, and we repeat this process for all pairs of rows to build the adjacency relationships. For this final example, since the height of the wall is just 1, we do not need to use the recursive dynamic programming approach. The total number of ways to build the wall is simply the number of valid row configurations for the given width. In this case, there are 8 configurations for width 5, so the output is 8. This completes the solution walkthrough for the problem. The time complexity of our solution can be understood by breaking it into 3 major phases: generating valid row configurations, pre-computing adjacency relationships, and using dynamic programming to count the number of ways to build the wall. First, in the phase of generating row configurations, the generate_row_configs function determines all possible ways to construct a row of the given width using bricks of sizes 1 and 2. This process is analogous to finding combinations of numbers that sum to the width, which grows exponentially with the width, similar to the Fibonacci sequence. Therefore, this step has a time complexity of O(2)width. Next, during the adjacency pre-computation step, we check if pairs of rows are compatible by comparing their seam positions. Since there are approximately O(2)width valid configurations, checking all pairs involves n² operations, where n is the number of configurations. Additionally, for each pair, we iterate through the seams, which adds a factor of width. This results in a time complexity of width for this step. In the dynamic programming step, we calculate the number of ways to build the wall using the pre-computed adjacency list. The dp state is defined by a specific row configuration and the remaining height of the wall. For each of the n row configurations, we explore its compatible transitions, which again involves n operations on average. Repeating this process across all height levels leads to a time complexity of height*n*n, or equivalently, height*2*width, which simplifies to height*4*width. Combining the complexities of all 3 steps, the dominant terms come from adjacency computation and dynamic programming. This gives us a total time complexity of width*width plus height*4*width. Simplified, it becomes width plus height, which accounts for the exponential growth in configurations and the linear scaling with width and height. Now, let's analyze the space complexity. During the generation of row configurations, we store all valid configurations in memory. With approximately O(2)width configurations, and each configuration using width space to represent the brick arrangement, the total space required for this step is O(2)width*width. For pre-computing adjacencies, the adjacency list maps each row configuration to a list of compatible rows. In the worst case, each configuration could be compatible with all others, resulting in n² storage, or equivalently width. Finally, in the dynamic programming step, we use a cache to store intermediate results for each state, which is defined by a row and the remaining height. With O(2)width rows and height levels, the space required for caching is O(2)width*height. When we combine all the space requirements, the dominant term comes from storing the adjacency list, which requires O(width space. Adding the caching space from dynamic programming, the total space complexity becomes O(width plus 2)width*height. To put this in perspective, consider a brute force approach where we generate all possible brick arrangements for a wall of dimensions height by width. This would involve checking every possible configuration, resulting in a time complexity of 2 caret height asterisk width, as the number of ways to fill the wall grows exponentially with its area. The space complexity for storing a single wall arrangement in this naive method would be height asterisk width. In contrast, our optimized approach avoids this exponential blowup by pre-computing valid row configurations and using an adjacency list to restrict transitions to compatible rows. Dynamic programming further reduces redundant calculations, making the solution much more efficient. Compared to the brute force approach, the optimized solution achieves a significant reduction in time complexity, from 2 caret height asterisk width to 4 caret width asterisk width plus height. While the space complexity increases to 4 caret width plus 2 caret width asterisk height, this trade-off is acceptable given the considerable time savings. Importantly, the best, average, and worst-case complexities all align with the derived bounds, as the algorithm exhaustively handles all possible configurations regardless of specific inputs. The mathematical foundation for this solution lies in the exponential growth of row configurations, which follows a recurrence relation akin to the Fibonacci sequence. By leveraging these pre-computed configurations and systematically building the wall using dynamic programming, the algorithm achieves optimal performance while ensuring correctness across all cases. One common mistake to avoid in this problem is misunderstanding the sturdiness condition. Many assume that a wall is sturdy as long as it fills the given dimensions, but that's not enough. The key requirement is that no two vertical gaps in adjacent rows align. If they do, the wall becomes unstable and would collapse. This is a crucial rule that must always be enforced to ensure the solution is valid. Another frequent error lies in how row combinations are generated. Blindly generating all possible rows without eliminating invalid ones early on leads to exponential growth in computation time. This makes the solution impractical for larger inputs. Additionally, failing to use memoization or dynamic programming is another pitfall. Without these techniques, the same states are recomputed multiple times, which wastes time and misses the opportunity to optimize overlapping subproblems. Finally, be careful with the base case in your dynamic programming table. For instance, if you forget to account for the fact that the first row has complete freedom of choice, errors in initialization will propagate through the entire solution, leading to incorrect results. Another common oversight is neglecting modular arithmetic. Since the problem may involve very large computations, the results need to be taken modulo 10 to the power of 9 plus 7 to avoid overflow and adhere to the problem constraints. Missing this step can lead to incorrect outputs for large inputs. For interviews, it's crucial to focus on the sturdiness rule. Demonstrating a clear understanding of why vertical gaps must not align across rows will show that you grasp the core constraint of the problem. Scalability is another important aspect to highlight. Using dynamic programming and memoization effectively reduces redundant calculations, making your approach viable for larger inputs. You should also be ready to discuss trade-offs, such as pre-computing valid rows and transitions, which improves runtime but consumes more memory, versus computing them on the fly. Finally, thinking recursively will help you break the problem into manageable parts. For example, you can focus on constructing a specific row based on the constraints imposed by the previous row. This approach aligns well with dynamic programming techniques. This problem shares similarities with several other LeetCode questions, which can help you deepen your understanding. For instance, LeetCode number 790, domino and trimino tiling, involves similar principles of tiling and modular arithmetic. LeetCode number 2328, number of increasing paths in a grid, focuses on counting paths under constraints, much like enforcing sturdiness rules in this problem. Another relevant problem is LeetCode number 62, unique paths, which also involves counting ways to achieve a target configuration while adhering to specific constraints. Lastly, LeetCode number 94, binary tree inner traversal, offers excellent practice for recursive approaches, which are often crucial in solving dynamic programming problems like this one. Exploring these related problems can reinforce your understanding of the techniques and principles involved. There are also alternative approaches to solving this problem that you might consider. One option is to use a state transition graph. In this method, valid rows are represented as nodes, and transitions between rows are represented as edges. Graph traversal techniques like breadth-first search can then be used to count all valid paths. While intuitive, this approach may require more memory to store the graph representation. Another method involves using bit masking to represent row states. This can optimize space and simplify transitions between rows, but it comes with its own challenges. Bitwise operations, while compact, can be tricky to implement and debug correctly. For smaller inputs, brute force is also an option. You could generate all possible walls and filter out the invalid ones. However, this method becomes infeasible as the dimensions of the wall grow, due to its exponential time complexity. By understanding these approaches and their trade-offs, you can choose the one that best fits the problem's constraints and requirements. Great job following through to the end. To wrap up, we reviewed the solution to a challenging dynamic programming problem, highlighted key takeaways, and discussed the importance of modular arithmetic and edge case analysis. Thanks for joining me, and I hope to see you in the next session. Don't forget to like, subscribe, and share if you found this helpful. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!